In the last module, we had talked of fluid particle acceleration, and we had written material derivative, the operator capital D by dt was given by d by dt of any quantity plus u times d by dx of this plus v times d by dy of this quantity plus w times d by dz of the quantity. So, this was material derivative. Now, and we had defined two frames of reference, Lagrangian and Eulerian, and we had discussed several examples to understand the difference between the two frames of reference methodologies. Both of these are used in fluid mechanics and thermodynamics and depends on what we are trying to do. So, if I am talking of a balloon, say for example, I have a balloon, and this balloon it has some amount of gas in it. So, I just do not tie the end and release it into the atmosphere. What will happen is the balloon will change shape and also the size, and this mass, some of it will actually go out of the system or of the balloon, which I am showing here the control volume as dotted green. The dotted green here has changed its shape and some of the mass has come out. So, let us call this M1 which is remaining and M2. We will say M1 plus M2 which has come out is your total mass M. So, if I have to do the analysis of what was inside this balloon which was M, now after I have released it, this was at time t, now it is at time t plus delta t, it is now M1 inside the balloon plus M2 which is outside. This is a very simple example, but hopefully this will illustrate the concept. So, this air had certain energy by virtue of having a certain temperature. So, mCpt would have been the energy content at time t. Now, it is m1 cpt inside the balloon, and what has gone out is m2 cpt. So, when I have to do the budget, I have to take care of what is now inside the balloon and what has come out. Now, by definition, system refers to a fixed mass. So, when I say a fixed mass, the m which was there originally, wherever it goes, m1, m2, wherever. So, this was my system initially. I will have to track this entire mass. Suppose there are 100 particles, 50 particles or 60 particles remain, 40 have come out. This 60 plus 40 is the system. So, I have to track what is happening to each of the particle to know how the system has changed with respect to time or with respect to space, position, whatever you want to call. It is like telling, in a class, if I have for 50 students and they come to a class in fluid mechanics or heat transfer, and you want to see what they do throughout the day. So, you put a chip and then you can track them. So, you keep a record of time t, 0, 1 minute, 2 minute, all the way for 24 hours, and you see what they are doing. This is for student 1. You can do this for all the students, okay, student 50. So, you will know where they are going, what they are doing, what they are eating, where they are sleeping, etc. Tracking every particle. So, ultimately I will have data for all the 50 students. System analysis would help me understand what is happening to everything related to the system. But now in engineering that is not practical, because if I am having say a turbine or a pump or something where the flow is going from this inlet to the exit, afterwards it goes to the generator and goes to the atmosphere. So, it is not practical to follow a fluid particle or a system. That is where the control volume analysis comes into effect. So, control volume refers to a fixed region in space where I allow mass to come in and mass to go out. And when I say mass, it is very important that we as teachers as well as for students, we tell them mass is a notional quantity, in that mass refers to amount, kgs, whatever you want to say, mass flow rate, kg per second. But please remember, it is a carrier of momentum, it is a carrier of energy. So, when I say mass, I am also talking of transport of momentum, transport of species, transport of energy. So whatever is applicable in this discussion to mass is also applicable to energy and also applicable to momentum. So when I have a system, so if I think of a system and a control volume, so this Reynolds transport theorem, which called RTT or Reynolds transport theorem, relates the system analysis to a control volume analysis. What does that mean? So if I take this balloon only, let us say this is my balloon, and balloon has this is at time t plus delta t, it has become smaller. Okay, so mass has left the control volume. This is my control volume, fixed region in space whose shape is also changing with time. Now I have varying combinations, control volume, shape same, shape changes with time, t and position x, y, z. So as the balloon just goes up, its shape also changes, and with time also it is changing. Engineering control volumes, if you are talking of flow through a nozzle, nothing is changing, the shape is not changing with respect to time or position. So this is the control volume whose shape remains intact. So we are just giving this example, and then we will go to a control volume which doesn't deform with time. So if this had say 100 particles and then 40 has come out here and 60 remain here, I do the analysis for the control volume. What was it at time t? 100. What is now at time t plus delta t? 60. What has left the control volume? 40. So these 40 have carried away energy, momentum, mass. So when I do the budget, I have to take care of amount before, amount after, and relate the two. Because who is transporting this energy and momentum? Mass flow. System is fixed mass. Fixed mass means m, not m dot. What are the units? Kilograms. Mass flow rate is m dot. The what is flowing, what is the carrier of momentum and energy? Mass flow rate. So original mass was say 100, mass 1, new mass is say 60. Change in mass is delta m, which is equal to 40. If you write your conservation of mass, dmcv by dt is equal to sigma m dot I minus sigma m dot E. Remember this equation, nothing is coming in, so you say dmcv by dt, rate of change of mass of the control volume is equal to m dot E. Mass flow rate that is leaving, therefore change in the mass of the control volume is negative integral mass flow rate dt. It went out at a particular rate, integrated over the time 0 to t, gives me the mass that has left, which is 40 units. Okay, so control volume, we are taking a fixed region. Out of that, the budget which is being done is for 100, which was the original system. What is going out is 40, what is remaining in the system is now 60. Now you extend this analysis to a control volume which is at arbitrary shape, it has multiple inlets and outlets, and let it deform, become however, mass comes in, mass goes out. So there is one m dot 1, there is one m dot 2, there is one m dot 3. Same thing, it's changed this shape, and also the masses are going to come in and go out. So this is at time t plus delta t. So how do I budget this quantity? It is like your savings bank account. You know, when you have 1000 rupees at the beginning of the month, first of every month, then you get your father gives you 5000 rupees, then it's your birthday month, so you get gifts which is about 3500 rupees. Okay, then you have credit card bills, this is something around 4000 rupees, then this is eating out, this is some 2000 rupees. At the end of the month, you do a budget. So mass coming in, momentum coming in, money coming in, money coming in, money going out, m dot out, mass, energy, whatever you want to call. So at the end, on 30th of the month, you will say, okay, original was 1000, plus 5000 plus 3500 minus 4000 minus 2000. What is the budget? 6000. So it is 3500 is the new mass in the control volume or new amount in the account. So this same logic we are going to use for in this so-called derivation of the Reynolds transport theorem, where we relate what is happening between a system and a control volume. So let us take an arbitrary shape. This shape has nothing specific or great about it. We are just going to take a shape which looks like this, and we will skip some amount of maths in view of time, but we will do the physical explanation in great detail. Okay. So this is a diverging section just for the sake of it. We have V coming in, V1 and V2 going out. The shaded region shown in purple and the shaded region shown in green. So these are two different things. So if I want to say this is 1, this is CV minus 1 and this is 2. I will explain that. So at time t, system is the same as control volume. What is system? System is a fixed region in space. Fixed region in space. Control volume is a fixed region in space. System is fixed mass. So at time t, this is going to be the control volume as well as system. CV at time t and system at time t. Now at time t plus delta t, this is the new time. So at new time, what is happening is the flow has taken place and some amount of mass from the original system has left. Some amount of mass from the original system has left. So let me show this here. At time t, this is my time t, this is my system and control volume. And at time t plus delta t, the green one is the new system at t plus delta t. Why is it not the control volume? Because control volume is a fixed region. So if I say A, B, C, D, CV is always A, B, C, D. Control volume is always A, B, C, D. The system initially was A, B, C, D. Now it is E, F, G, H. So system at time t, system is the same as A, B, C, D. System at time t plus dt is E, F, G, H. Why? Because certain amount of mass which is given by this shaded region has left the control volume and gone out. Okay, has left the control volume and gone out because of the flow. So what I want to say is CV minus 1, this was the CV, ABCD was CV initially. So CV minus shaded area 1, CV minus shaded area 1 plus the shaded area 2. This is 1, this is 2, which I have shown in this figure. CV minus 1 plus 2 is nothing but system at time t plus delta t. Okay, where shaded area 1 is inflow into the control volume from time t to time t plus delta t. This is basically because of mass flow. Balloon, suppose the balloon was being filled in by a pump, so I had a thing to fill in, and also there was a leak. So balloon filling in is m dot in. The balloon leaking is m dot out. So if the m dot out and m dot in were equal, the balloon's shape would not change. If the m dot in was greater than m dot out, the balloon shape would become larger. Vice versa, if m dot out was larger than m dot in, the balloon would shrink in time. That is what we are saying. So the mass that is coming in is represented by I. Number 2 is outflow from the control volume from time t to t plus delta t. Again, please remember, control volume is a fixed region in space. So A, B, C, D system at time t, control volume at time t. E, F, G, H is the new system at time t plus delta t. A, B, C, D is the control volume at time t plus delta t. Why? Because control volume is invariant. That is the thing that you have to tell students. And now what is left is only maths. So consider any extensive property. What is extensive property? Extensive property is some property which depends on the mass. So it could be total energy, total enthalpy. So we will take any external property B such that the corresponding internal property is the extensive property divided by M. So what we are saying, so this can be applied to B is energy, momentum, mass, or any other quantity that may be of interest. Okay, so now we have some maths. So at time t, what are we writing? At time t, B of the system, the extensive property of the system is same as the extensive property of the control volume, because system and control volume coincide. Because these two coincide, this is given by A, B, C, D, this is going to be the same. Now at time t plus delta t, B of the system at t plus delta t, this step is what is important, and we have already seen this from this diagram. Okay, the system has moved, has changed this shape because you are tracking the same mass, the same 100 particles are being tracked. Out of the 100, 80 are still inside the control volume, 20 have left, some new 20 or 25 have come in. So B of system at t plus delta t is nothing but, using this definition, CV minus 1 plus region 2, that is nothing but BCV at t plus delta t minus B of region 1 at t plus delta t plus B of region 2 at t plus delta t. Now what we are going to do is subtract first from the second and divide by delta t. We are going to divide by delta t. Why? Because I have the definition f of x plus h is equal to f of x plus h minus f of x is equal to f prime of x. So f of x plus h minus f of x, this is 2 minus 1, divided by h, which is your delta t, that gives me the derivative of the quantity of the function f with respect to x. So therefore I write B of system t plus delta t minus B of system at time t divided by delta t is equal to B control volume at t plus delta t minus B control volume at t divided by delta t. This is these two variables, and what is left is plus B2 t plus delta t minus B of 1 at t plus delta t divided by delta t. 4 terms are there, 2 have come under the green and the 2 are just like that. This quantity by definition is derivative of B of the system. So dB of the system with respect to t is equal to same thing for the control volume, dB of the control volume with respect to T, and dB of the control volume with respect to T minus plus B2T plus delta T divided by delta T minus B1T plus delta T divided by delta T. Sorry, I am using delta T this way. You can just make it delta T here, delta T. Okay, so dB of system. So this is going to be the derivative. So Bi, B1 and B2 we are going to say. This we have tracked as change of B within the system over time delta T. Change of B within control volume over time delta T. What is left? These two terms. B, any extensive property. So let us say it was total energy. Total energy over time delta T divided by delta T is nothing but what is being brought into the control volume because of the flow. What is coming in because of the flow is what is represented by these two quantities. So B2 is what is coming out. So quantities, we will write this mathematically, quantities due to mass, flow and the associated intensive property B. Okay. So the mass flow rates, as I said in the balloon, could be different. When m dot in and m dot out were different, the balloon would shrink in size, the energy content, everything would change. So B is what now we have to look at. So this quantity B can be written as B of 2, let us take, is written as rho 2 B2 A2 V2 into delta T. This is what? M dot B2, M dot 2 B2 delta T. Mass flow times the intensive property over that time. So mass flow times intensive property over delta T. Mass flow rate over delta T would give you the mass times the intensive property would give you the total extensive property. Therefore, B dot out, this is leaving the control volume, the number 2 was outside. Remember the diagram, number 2 was here. This is flow out. So B dot out is rho A2 V2 B2 delta T. Therefore, we have B2 T plus delta T over delta T is nothing but rho 2 A2 B2 delta T divided by delta T is nothing but rho 2 A2 V2 B2, or if I want to write in a form that we are familiar with, m dot 2. This is coming out. B dot in, on the other hand, is mass flow coming in, which is similarly going to be rho 1 A1 V1 B1. Okay. So now I put these things together here. dB of the system with respect to dt is equal to dB of the control volume plus B dot out minus B dot in. B dot out minus B dot in. Mass flow rate m dot 1 B1, that is why these dots are there. Students sometimes say m dot is m by t. This is absolutely incorrect. Mass flow rate is not mass of the system divided by change in time. It is not that. It is, we showed it here also. This is how mass change has to be calculated, not by saying m dot is m by t. That is not the way. This quantity, this is related to the system, this is related to the control volume, this is what is coming out, what is coming in. This can now be changed to what we call as the material derivative, and I will explain in a minute why. This was a region which was fixed like this. Okay, the system was just changing with respect to time, but the system in reality, as we said in the case of a balloon, where the balloon is just left like that, you can have the system changing its shape due to position as well as with respect to time. So this material derivative, remember the definition of material derivative we had shown here. Material derivative is nothing but where we have the change with respect to time, with respect to positions. This change is going to be reflected by this term. How the system is changing with respect to time as well as with respect to position, and that is essentially related to the convective transport that is happening with the system. This one is nothing but what is there for the control volume, dB Cv by dt plus B dot out minus B dot in. This form is not yet useful, so we are just going to write the form that we like. This is now going to look as it is, B dot in, B dot out minus B dot in. And if we write for mass flow rates as which was seen before, dB of the system, so material derivative of the system with respect to time is equal to dB of the control volume with respect to time plus, if I write this as integral over the control surface, which is rho V dot n cap dA. This is mass times B. I will explain this. Integral over the control surface. This was the sign convention which was introduced. Mass flow coming in, m dot in, was treated as negative because the vector unit normal was opposite to the direction of flow. Unit normal is like this. Inlet velocity is at 180 degrees, so cos of 180 is minus. So all the inlet velocities were treated as negative. All the velocities leaving the control volume were treated as positive. So the intensive property which is coming in, B1 into M1, M dot 1, that is coming in, whatever is going out, when you sum that up over the control surface, you would have couple of streams coming in, couple of streams going out. So this integral, rho V dot n cap dA is the mass flow rate. Rho V dot n cap into BdA is mass flow rate times that intensive property. So if you have an IC engine, air is coming in, fuel is also coming in. So this is m dot air, m dot fuel. Each will have a particular enthalpy coming in. I am just writing HA and HF. This could be a more complicated form. The energy brought in is related to the mass flow rate of the individual species. It may be the same species, it may be multiple species which is coming into the control volume, doesn't matter. You have to, the important thing is the pair, B times m dot. So if it is air, it is associated with the enthalpy of the air. If you are talking of a single stream, multiple streams of water coming into a heat exchanger, this is m dot 1 at 30 degrees, m dot 2 at 60 degrees. You multiply the enthalpies appropriately. So it's same water, and this is also m dot 1 plus m dot 2. So what is important is the enthalpy or momentum brought in by that particular stream. That is the second and the third term are put together here. This, when you write, this is going to be integral over the control volume d by dt. Capital B is B times small B times mass, which is nothing but B times rho into dV. dm is rho into dV. So what we are going to say is dB Cv by dt, dB Cv by dt is integral d by dt over the control volume of rho B dV. Rho into dV was the mass, mass into B is capital B. Rate of change of this quantity over the control volume with respect to time. So, what is happening to the quantity that was inside the control volume? The control volume, remember, is a fixed region in space. So, if you are talking of a steady state problem, in thermodynamics students would have seen, these are examples which we can give. Unfortunately, students don't connect to what has been studied before. So, we have steam flows through insulated turbine. So, steam flow is given 5 kg per second. The mass flow in is same as mass flow out. The enthalpy that it comes in, you go to the steam table, superheated steam, you take out the enthalpy at 540 degrees centigrade or whatever. So, this is H in. Then we have done the analysis, we get m dot hi minus h dot e is equal to work done by the control volume or work that is obtained. Where is it coming? It is coming from this expression only. Mass flow rate happens to be the same. Now, suppose there was steam bleeding out here, you say m dot 2 goes out at some intermediate pressure, it has some intermediate enthalpy, and m dot 3 is equal to m dot 1 minus m dot 2. All this is done at a subconscious level, and this comes out at a different enthalpy m3. All that is taken care by this. Unfortunately, we do a specific case first and go to the most complicated general case at a later stage, and students do not connect the dots. That is the biggest problem. So, the complete Reynolds transport theorem will now look like dB system by dt is equal to d by dt over the control volume rho b dV plus integral over the control surface rho b v dot n cap dA. This is something students can be told to remember. More importantly, rather than memorizing it, you can say rate of change of the extensive property with respect to time, more importantly for the system. This is rate of change within control volume, and this one is change due to mass coming in and leaving the control volume. Okay, leaving and coming in are both taken care by this integral over the control surface. Keep in mind, negative is for mass in, positive is for mass out. Correspondingly, energy coming in will be treated negative, momentum coming in will be treated negative, energy going out will be treated positive, momentum going out will be treated positive. If you remember, if the students appreciate this expression, there is nothing to memorize, everything will fall automatically. All you have to do is demarcate a control volume properly, demarcate a system, and then the analysis just is a mathematical progression of thought process. So, steady state system, and there will be always a difficulty for students which term to cancel for steady state. So, when I say steady state, d by dt of any quantity is equal to 0. dB by dt of the system will be 0 because by definition, when I talk of a system, by definition system is a fixed mass. So, this is going to be 0 because system is fixed mass. This has nothing to do with concept of steady state. Whereas, d by dt of this integral, second term which I have written, that is d by dt of integral rho b dV, this would be 0 at steady state. What does that mean? Go back to this example. Mass flow is 5, mass flow going out is also 5. Whether it goes out as steam bleeding here or this way, whatever is coming in is going out. There is no net change in the control volume mass. Or if you go back to your again thermodynamics, unsteady thermodynamics problem, we had dmCV by dt is equal to minus m dot E, the balloon problem. There mass flow was not there, mass flow out was there. So, mass of the control volume was decreasing with respect to time. So, this quantity again my example is with respect to mass flow, you can have it with respect to enthalpy, internal energy, whatever. So this quantity will be non-zero in case of unsteady only. In case of steady state, this term will be 0. d by dt of this quantity will be 0. This quantity number on the right hand side, which is integral over the control surface, is going to be related to mass flow coming in, mass flow going out, and the corresponding intensive property B that is being brought in. So this Reynolds transport theorem is a very powerful tool, and later on in the subsequent modules you will see the use of this Reynolds transport theorem to derive the conservation of mass, conservation of linear momentum. There can also be a derivation where you derive conservation of angular momentum, but that will not be done in this course. Conservation of energy. Remember, conservation of momentum, linear momentum, where momentum being a vector quantity, you would have three equations, one x component, y component, z component. So you will use this formula, the Reynolds transport theorem, for u, for small v, and for w. Whereas for energy equation, energy being a scalar, you would have the intensive property and the extensive property denoted by capital E and small e, and then you will do the derivation for conservation of energy. So with this, we will, in the next module, we will start the conservation of mass followed by conservation of momentum and energy. Thank you.